Hey guys, my name is Hamza Rana and this is part 1 of a 4-part series that I'm uploading on YouTube about quantum mechanics and the features of our universe. So before we get started, I want to start at the very beginning. The very beginning of space and time itself, the Big Bang. Now what exactly was the Big Bang? You've probably heard of it either in your science class or on social media, or maybe even while watching the popular comedy show called The Big Bang Theory. Okay, so as I said before, the Big Bang was the beginning of, well, everything. Space, time, everything that you see around you. Now while it can't be proven because we don't have the technology that allows us to travel back in time to see the origin of the universe, most scientists have come to realize that this is actually in fact true, because we can make certain observations about what we can already see in our universe. And based off of those, this theory is pretty accurate. Now the theory states that our universe originated 13.8 billion years ago. That's a really big number. It says it originated from a single singularity. But what exactly is a singularity? Well, imagine the entire universe as we see it now, shrunk down into a tiny space. Maybe about the size of an electron. So a singularity is a hypothetical area in space and time where all laws of physics are broken down. It's a place where there is a large amount of mass compressed into a very small area, meaning that it practically has an infinite density. Now, what happened was that during the Big Bang, this singularity basically exploded and underwent rapid expansion. We don't know why, but we know it happened. It quickly expanded to the size of the universe that we see now, and as it was expanding, there was a lot of heat released. Scientists theorized that in the first second after the Big Bang, the universe was approximately 10 billion degrees Fahrenheit. To compare, our sun is only 10,000 degrees Fahrenheit, so this was a lot hotter. Now this extremely hot soup, as scientists call it, contained electrons, protons, and neutrons, along with their antimatter counterparts. So what happened was that while it was expanding, the electron and anti-electron pairs annihilated each other and created light, or photons. After they annihilated each other, there were more protons and neutrons than electrons. So what happened was protons and neutrons combined to form basic elements such as hydrogen and helium. So as this was happening, the universe was also rapidly expanding, which means that the total heat was decreasing. How is this, you may ask? Because heat can also be described as the rate at which particles are colliding with each other. If the volume is less, the particles are closer together, meaning they're more likely to collide, thus the heat is greater. But if you increase the volume, the space that the particles have to move around also increases. That means they're less likely to collide and the total amount of heat decreases. Now you might be wondering that how do we exactly know all of this about the Big Bang? Well, there are two phenomena. One is the Doppler effect and the other is the cosmic microwave background radiation. I know it's a big word, but we'll get into that later. So first, what exactly was the Doppler effect? Okay, now Doppler effect is a crucial part of the Big Bang theory. Without it, we wouldn't even have figured out that the universe was indeed expanding. A simpler way to explain this phenomenon is to go outside and see a car pass by, and this car is constantly honking its horn. I know it's kind of annoying, but I mean, we have to see this phenomenon, so let's go outside. Actually, wait, I can just do this. Now the car is going to pass by with a constant horn, so let's watch that and see what happens to the sound in the pitch. What happened was the sound had a higher pitch when it was coming towards us, but had a lower pitch when it was going away from us. This is because when the car is moving towards us, the sound waves are bunched up together and are closer, meaning they have a higher frequency and thus a higher pitch. But when they're going away from us, the waves are spread apart and thus have a lower frequency and a lower pitch. The interesting thing about this phenomenon is that it doesn't apply to only sound waves, it applies to all waves, including light. That's one of the reasons we were able to figure out that the universe is expanding, because stars emit light. So using the phenomenon, we can tell what the momentum of the stars actually is. And that's basically the effect in a nutshell. Now what some astronomers noticed back in the 1920s was that all the stars that we could see in the sky were slightly redshifted. What this means was that the frequency of light that we were receiving from these stars was shifted towards the lower end of the spectrum. That meant that based on the Doppler effect, these stars were moving away from us. But it wasn't just us, like we weren't the center of the universe or anything. It was everything was moving away from, well, everything. The entire universe seemed to be expanding. Now based on this effect, we can come up with a theory that At the beginning of all time, the universe was at a single point. Something happened, caused it to explode, and the universe expanded. Now, the technical details like the temperature and the age of the universe, they don't come from this part of the Big Bang Theory. They come from the cosmic microwave background radiation. But what exactly is this radiation? Now, the cosmic microwave background radiation was discovered by accident, which is kind of funny. It was discovered by two scientists, Arno Penzias and Robert Wilson. They, at the time, were building a radio receiver at Bell Laboratories in 1965. After completing the construction of the receiver, when they checked the readings of what the receiver was actually picking up, there was some anomaly. It was picking up higher temperatures than it should have. So they figured maybe it was some external factor that was causing that to happen, such as pigeons or their nests or something like that. So after eliminating a couple of them and cleaning up their poop and eradicating their nests, the anomaly still existed. They realized that they were picking something else, something that was prevalent in our universe. But after consulting a couple of other scientists, they figured that this thing that they were picking at these higher temperatures, they were actually the background radiation that was caused by the Big Bang, and that still exists throughout the universe. This was one of the most crucial discoveries that was made in the 20th century. But sadly, those poor pigeons had to give up their lives for this to happen. Now, through this cosmic microwave background radiation, or CMB, we were able to figure out how old the universe actually was. How exactly is that possible? Well, light has a fixed speed at which it travels at. The further the source of the light, the longer it will take to reach us. And this light that's reaching us, it's carrying information about the source. So say the light takes 100 million years to reach Earth. Now, when it eventually does reach, we would be seeing that star or that source of light 100 million years in the past. Which basically means that the further out we look into the universe, the further back in time we're actually seeing. And since this background radiation, this cosmic microwave background radiation, is the oldest light in the universe, we can essentially get information about its source, which was the Big Bang. We can see what the Big Bang was like, we can know its features, we can know how old it was, what the temperature was, things like that. And through this phenomenon, we were also able to understand not only the origin of the universe, but the origin of different galaxies, different structures, different features of this universe. And of course, it allowed us to calculate the basic parameters for the Big Bang Theory. Now that we've discussed what happened at the beginning of all time, what's going to happen at the end? Where are we headed? Well, scientists have come up with three main theories. The first one is the Big Crunch theory, which states that the universe will eventually reach a maximum point and stop expanding. At that point, gravity will cause the universe to actually begin contracting and will collapse to a singularity again. The second one is the Big Freeze theory, which states that eventually the rate of expansion will not decrease, it will be constant, right? So the universe will keep on expanding until there's only singular objects that remain in space. Planets, stars, they'll be all alone, there'll be nothing orbiting anything, there'll be no galaxies, nothing like that. And it will be so far that light nor heat will be able to travel from place to place. So it'll become cold and it'll become dark, and the temperature will reach 0 Kelvin, which is absolute zero. Last one is the Big Rip, where the rate of expansion actually increases and it causes planets to rip apart and all structures will be destroyed, but only singular particles remain. So even atoms will break down to just their subatomic particles. Maybe even those will break down just to their quarks. You never know. But which one of these theories are we headed for? There's just three possibilities. Which one are we more likely to experience? Well, the fate of our universe depends on two different variables. The first is the rate of expansion. Now, the current rate of expansion of our universe, as scientists say, is too slow to head for the Big Rip. So we know that's not going to happen. What about the other two, Big Freeze and the Big Crunch? Well, in order to figure that out, we need to look at the average density of our universe. If the density of our universe is greater than a certain critical value, we're headed for the Big Crunch. But if it's less than the critical value, we're headed for the Big Freeze. So scientists currently say that our average density is way less than a critical value. But there's a problem with this calculation. This average density that we've calculated, it only counts for the visible matter that we see. So stars, planets, galaxies, things like that. But what about the matter that we don't see? What about dark matter? What about dark energy? That is also a huge part of our universe. But currently, we don't have the means to detect this dark matter and calculate exactly how much there is. So we can't really say which of the theories we're actually headed for. There might be enough dark matter for the big crunch to occur, or there might not. There is no way of telling. But either way, the end of the universe isn't likely to happen for this many number of years, so you're probably fine. There's nothing to worry about. Now, I know this was a lot of information to grasp in such a short time, but I hope I was able to explain it well and it made sense. Let me know what you guys thought in the comments below, and if you guys have any feedback for me on how I can improve my videos. And I'll catch you in the next one.